Hello again. We need to discuss the work of Nicolaus Copernicus, as he created a springboard for Kepler's jump into modern science. Copernicus is renowned for his revolutionary idea of placing the Sun rather than the Earth at the center of the universe. And while he wasn't the first to conceive of this, with Aristarchus of Samos proposing it 3 centuries BC, Copernicus was the first to thoroughly detail his model. His masterpiece is the book De Revolutionibus Orbium Celestium, on the revolutions of the heavenly spheres. By around 1514, Copernicus had already drafted a text outlining the heliocentric view that he would later expand in De Revolutionibus. This early work, known as Commentariolus, was only shared among friends. He was undoubtedly aware that proposing a moving Earth out of the center could provoke controversy or even jeopardize his career. Central to Commentariolus were 7 axioms, similar to Euclid's approach to geometry, and these offer a comprehensive description of his model. Let us briefly discuss these axioms. 1. There isn't a single central point for everything. 2 and 3. The Sun is at the center, but not everything revolves around it. The Moon orbits the Earth. 4. The stars must be incredibly distant away, since no parallax is observed even at the Earth's 2 extreme position, winter and summer. This maybe requires some explanation. When you look at an object with one eye and then the other, it appears to shift, unless it is very far away, compared to the distance between your eyes. And this so-called parallax effect allows us to perceive that and enables astronomers to measure distances, though they are able to measure from different positions on Earth or even at different positions off Earth during summer and winter. And despite this, despite the huge distance between summer and winter of the Earth's locations, no parallax is observed. 5. And this simple explanation dismissed the hard-to-believe concept of a huge crystalline sphere rotating at very high speeds with all the stars in it. Nevertheless, many objected to the idea of rotating Earth. Question: why don't we experience constant storms, get flung off the surface, or why objects fall vertically? The answers were available, but took time to dispel skepticism. 6. The Earth has more than one motion. Most people associate Copernicus primarily with the Earth's revolution around the Sun, but the rotation around its axis is actually of far more impact, giving us day and night and the primary movements of the stars. It turned out to be a hard sell to give the Earth not only one but even 2 movements, and as we shall see, he had to add a 3rd. 7 and last, a significant advantage of the heliocentric model was its very elegant explanation of retrograde motion that was occupying many minds. No epicycles needed. Imagine observing Mars, represented by this lady in red, from Earth. While she moves forward, she appears to temporarily move backward against the stars, the clouds, when Earth overtakes Mars. And this also immediately explains why retrograde motion is only observed when Mars and Earth are closest and lined up with the Sun. I believe that this, along with the elimination of that hatred equant, forms the basis for the enthusiasm of many followers at the time. De Revolutionibus, published nearly 30 years later, essentially elaborates on this model to make it align with measured data. It consists of 6 chapters. The first chapter is an accessible introduction where he philosophizes about planetary system models and discusses his proposal. The rest is, let's say, a more challenging, detailed discussion of his model. In my opinion, his most revolutionary and brilliant ideas are beautifully summarized in the 4 pages of part 11 of the first chapter, A Demonstration of the Threefold Movement of the Earth. The first movement is the rotation around the Earth's axis, responsible for day and night. The second movement is the rotation around the Sun, similar to other planets. And this explains much about planetary observations, including retrograde motion. The third movement is more subtle and nicely illustrates the thinking at a time when many physics concepts had yet to be discovered. I wasn't aware of all this until I started reading De Revolutionibus in translation. This movement is related to the seasons. Copernicus knew the seasons were influenced by the inclination of the Earth's axis. That's the angle between the Earth's rotational axis and the orbit axis around the Sun. In the hemisphere directed towards the Sun, it's summer. If I'm the Sun, it's summer here in the southern hemisphere. If you understand the concept of rotation at the time, half a year later it would appear to be the same. Still summer at the southern hemisphere. And that's not all. Still winter on the northern hemisphere, my hemisphere. I'm so grateful for the law of conservation of angular momentum, because in reality the axis maintains its orientation. And half a year later it will look like this. Summer at the northern hemisphere. However, the concept of angular momentum, or even regular momentum, had yet to be formulated. Copernicus could only explain this within his rotation concept by assuming a third movement of the Earth, a precession rotation of its axis. Like this. Completing one full rotation in a year. Well, almost. We live in a time where there appears to be a stellar rotation point in the direction of the rotation axis. Very close to, at least. A very specific star is there, the pole star. But this point has been changing. And Copernicus knew that. He noted that this point had rotated 21 degrees since Ptolemy. Here you see the 21 degrees in the original book, as well as the mention of Ptolemy. 21 degrees in about 1400 years equates to a full circle in about 24,000 years, close to the 26,000 years that we now know it to be. Therefore, Copernicus had to assume that the precession rotation of the axis took slightly less than a year, about 22 minutes. To also explain that movement of that rotation point in the sky. If you think of it, it's quite captivating that Copernicus found out about the precession rotation of the Earth's axis, a real thing, but for the wrong reason and way too fast. His small correction is the real precession. The challenge was to build a model with the predictive power for the positions of the planets based on the discussed axioms, including strictly circular rotations at constant speed. In that sense, Copernicus was a true Aristotelian. However, the orbits are not perfectly spherical, and orbital velocities are not constant. And if you strictly adhere to spherical orbits at constant speed, the data won't fit. Therefore, to fit the data, tricks were needed. Copernicus eliminated the equant, but not the epicycles. Fewer than Ptolemy needed, but still many, and not just one per planet, and including epicycles. And he had to take different center points for the various planetary orbits, close to the center of the Sun, but not exactly at it, adding another complication. Nevertheless, it was seen as a significant step forward from Ptolemy's model. There's another thing worth mentioning. The heliocentric model and clever trigonometry allowed Copernicus to measure the relative distances of planetary orbits to the Sun, relative to the Earth's distance from the Sun. And these data would feature prominently in Kepler's work 53 years later. And that would be impossible to calculate within a geocentric model. All you need is a device to measure angles. Here is how Copernicus did it for Venus. By observing Venus from Earth, you can see it at different distances, expressed as angles, from the Sun. In a heliocentric model, when Venus is at its maximum distance, you have a simple geometric situation with a straight angle. And this allows the calculation of the ratio of the two distances as the sine of that angle. But it is not that simple, thanks to Aristotle again. In order to have a circular correction for the elliptical orbits, Copernicus had to assume slightly different centers of the orbits, points D and C here on his original drawing, with two positions with maximum angles. But you can still do the math if you measured these angles. And you see here Copernicus text and a modern algebraic way to derive. And thus, the radius of Venus' orbit would be 0.719 that of Earth, which is very close to the currently accepted value of 0.723. And to my surprise, all that great information is rather hidden in his work, not only for Venus but also for the other planets, and nowhere a nice table with all values. After publication of the Revolutionibus in 1543, no further progress was made. And that would change with the birth of a new star, a stellar nova, some 1,000 kilometers southwest and 28 years later. Stay tuned.